Okay, the number of protons in an element determines what it is. So hydrogen would not be hydrogen if it did not have one proton. You put one more proton in something, or you take a proton away from the nucleus, then you do not have that substance anymore. It's no longer carbon or nitrogen or whatever. So you have to have that number of protons that's going to define exactly what that element is. Now, what can vary and still be the same element is neutrons. So carbon can have 3 different isotopes, and each of them have a different number of neutrons in the nucleus, but it will never vary, the number of protons will never vary. So the number of protons in the nucleus is called the atom's atomic number, symbolized by Z. Okay, I'm not really sure why that is. But that, of course, is going to be unique to that element. The sum of the number of neutrons and protons is called the mass number, symbolized for some reason by A. You don't really need to know these symbols other than they might pop up in the homework and say this Z equals, and you'd have to realize that that's atomic number. Or they say A equals, and you'd have to realize that that is mass number. And this mass number is unique to that isotope, and that information is actually not found on a periodic table. And you know, if you take a look at your periodic table, which you should right now, what you'll see is that you have one number, the atomic number. That's a nice whole number, and it starts with hydrogen being 1, helium 2, and then so forth all the way up to wherever your atomic table ends. But you do see one other number, and that other number is looks like an average because it has like a decimal to a point that has numbers after the decimal. That is actually not the mass number. That is something else we're going to talk about, the atomic mass, but that is not the mass number. The mass number often for an isotope is not published on a table. It's not readily available. They'll give it to you in the problems. You could look it up in the Handbook of Chemistry and Physics, but it's not something that you know for individual isotopes, because elements can have 7, 8, 9 different isotopes and different number of mass numbers. So that's not something that's generally available. Okay, we use the symbol, and this did not come across when this got loaded, so let me go ahead and write it out like this, to represent an isotope. So we put the symbol here, whatever the symbol is on the periodic table, copper, Cu, carbon, C. The Z is its atomic number. Of course, we put that as a subscript. And then A, we put that particular isotope's mass number, which would be the number of protons plus the number of neutrons. So if we took A minus Z, we would know the number of neutrons in that particular isotope. Okay, so let's just take a look at some of the isotopes of carbon. And again, this didn't come across real well. So what that would look like is carbon-14 would look like so. You could also rate it as C14 because, quite honestly, that 6 is kind of redundant. We know because it's carbon, it has to have 6 protons. So that might be a little redundant, so writing it like this might be a little bit better. The whole number on the periodic table indicates that atomic number, the number of protons, and that's the whole number. Sometimes it's on top in the box, sometimes it's on the bottom. The number with the decimals after it on the chart is the weighted average of all the naturally occurring isotopes, and that is called the atomic mass. Now, I know these terms can be confusing, so take some time to just work it out for yourself. You've got mass number, which is this, protons plus neutrons for a particular isotope. But this atomic mass, which I know sounds very much like that, is different. It is, we take all the different isotopes, however many there are in nature, we average them, and that's where we get this number, the atomic mass. And we do a weighted average, which we'll talk about. But this is where we get that number with the decimals after it on the chart. And that is different than just one particular isotope of an element. Okay, so let's say we're looking at the 3 naturally occurring isotopes of carbon. And basically, we would know that carbon-12 would have 6 protons, of course, because it has to. be if it's going to be carbon. 12 minus 6 would give us 6 neutrons. And if it's neutral, and we haven't talked about anything not being neutral so far, it would have 6 electrons, so it's neutral. Protons and electrons being positive and negative, respectively. Carbon-13, of course, would have 6 protons. In this case, it would have 7 neutrons, 13 minus 6, and it would have 6 electrons if it was neutral. And you're not told anything otherwise, so you assume it's neutral. Carbon-14 in the same thing would have 6 protons, 8 neutrons, 14 minus 6, and 6 electrons. So, again, this did not come across, but let's rewrite it here. Iridium, atomic number 77, 77 protons. Okay, so we'd have 77 protons. We go 192 minus 77 to get 115 neutrons. And because we haven't been told any differently, there's no charge to this. By the way, the charge would be up here if there was a charge, but there isn't anything. We're going to know it's neutral, and so 77 electrons. Okay, now going to the charges a little bit. Sometimes we have an unequal number of protons and protons and electrons. The atom has either lost or gained electrons. Remember, you cannot mess with the protons, so this is going to be a deal where we're going to lose or gain some electrons. The protons stay the same. So, if the ion is positive, it has lost electrons. And I think visually that's probably a good idea to take a look at. Let's just take a look at lithium. Now, if you look at lithium on your periodic table, you see that lithium has an atomic number of 3. So there we have 3 protons. Now, there'd be some neutrons in here too, but we don't know which isotope we're talking about. So maybe there's 4 neutrons. Who knows? Okay. You cannot mess with the nucleus. So if I make it a lithium plus 1, which is what lithium often does, it's not like I can just go and say, hey, I'm going to add another proton. Well, then it wouldn't be lithium anymore. Okay, and you just cannot mess with the nucleus. But what I can do is I could remove one of these, and if I remove one of them, then lithium, overall, lithium plus 1, has 3 protons and only 2 electrons, overall leading to a positive 1 charge. Okay, so in the same sense, if I have negative, let's just take oxygen for instance. Okay, now oxygen is going to have 8, atomic number 8. So it'll have 8 protons, a bunch of neutrons in there too, but we'll deal with that in a minute. And so we have 8 electrons. Now, oxygen quite often will form an O minus 2. It's just what happens with oxygen. We'll take a look later why that is. Well, again, I can't just go ahead and take away protons. That just cannot happen. But what could happen is 2 electrons could decide to join the party for reasons we'll look into next. And that's exactly what does happen. So oxygen minus 2 ends up having 8 protons, of course, otherwise it wouldn't be oxygen. 10 electrons, and then depending on what isotope it was, we could figure out the neutrons. Okay, so we're going to look at several of these, and unfortunately they did not come across real well, so I'm going to rewrite them. This is 184, mass number 74. Okay, and so rewriting all of them like so, I'll rewrite the next one here too. We have 127 and 53, I to the negative 1. Okay, and then you can rewrite these last 2 here. All right, for tungsten, which is W, I've got protons, electrons, and neutrons. Tungsten, if we look it up, is 74, which we see right there. The electrons, now there's a plus 4, so it must have lost 4 electrons to give an overall plus 4 charge. And then for neutrons, I'm going to go 184 minus 74, 110. Okay, for iodine, I can look this up on the periodic table, or I see it right there, 53 protons. The electrons, it is a negative 1, so it must have gained an electron somewhere. So 54 electrons, and then I'm going to go 127 minus 53 to give us a total of 74 neutrons. Okay, for osmium plus 3, there would be 76 protons, 73 electrons and 114 neutrons. For Se minus 2, 34 protons, 36 electrons, because of that minus 2 charge, and 45 neutrons. Try those out yourself. All right, last thing we're going to do is we're going to calculate atomic mass. And remember that atomic mass, not to be confused with mass number, is the weighted average of all the naturally occurring isotopes. Usually the most common isotope will have the mass number very close to the average atomic mass on the periodic table. So because it's a weighted average, that's why that happens. We base all the atomic masses you see on the table based on carbon-12. We say carbon-12 weighs exactly 12 AMUs, atomic mass units. And then everything beyond that, less or more. Okay, so let me show you an example of the calculation. Carbon-12 weighs exactly 12 AMUs. It occurs 98.904% of the time in nature. Now, if you look at your periodic table, you will see that the number there is like 12.001 AMUs. That is reflective of the fact that most of the carbon is carbon-12. Now, there is a trace amount of carbon-13 that weighs 13.0034 AMUs. It occurs a little bit of time, or a little bit of the carbon, and carbon-14 weighs that. This is responsible for the carbon dating, but it's in such trace amounts that our instrumentation would not show it. Okay, so what I do is I take the 12 times that, plus, people have a hard time with that, plus the next isotope's mass times its abundance in decimal form. So 98 becomes 0.98, 1% becomes 0.01, okay? And we add every isotope we have, and what we should find when you plug that in, and absolutely do plug that in, you would find that. And the answer should be on the periodic table, so we get a little cheat sheet there. Okay, you can go back and you can check your answers. All right, so for this one, what I'm basically going to do for argon, I'm going to take 35.968. I'm going to multiply it by 0.00337, plus, I'm going to take the next isotope's weight, 37.963. I'm going to multiply it by its abundance, which is pretty little. Okay, be careful you're doing that correctly. Plus, I'm going to take the third one, kind of running out of room here, 39.962, and I multiply it by 0.996, 99.6%. 0.996. Okay, absolutely practice that out. What you should find when you do that is 39.947 AMUs, and that's exactly what should be on the periodic table, but check that for yourself. Okay, so for this one, what I would do, I'll just talk it out. I'm going to take that times 0.04, okay, plus I'm going to take 51.94 times 0.8376, okay, plus I'm going to take 52.94 times 0.0955, plus 53.94 times 0.0238. You should get what's on the periodic table, AMUs, okay, and absolutely do that yourself. Check it out. Okay, for this one, it's a little bit trickier. I don't have the atomic mass. I have two unknowns, which always throws people off. But just think about this. The abundance, if I only have two isotopes, has to add to be 100%. So that second number there shouldn't be too hard. All we're going to do is say it's 100% minus 80.20, and we'll get that. So then we have to find that out. All right, so following protocol, I'm going to multiply that by 80 plus, I'm going to do my unknown, I don't know, that's going to be 0.198. But, well, of course, what do I know the answer has to be? I have a cheat sheet, like I said. This is what's on the periodic table. Look it up. This is on the periodic table. Okay, so then what this becomes is basically multiply this, subtract it from that, then we're going to get 0.198x, divide both sides by 0.198. And you should get 10.009 AMUs. And please work all of these out. Don't just take my word for it.